All right, let's start here. Let's start with this problem. What did you get? Where did you get? There you are. You're going to find the double integral from 0 to pi, 0 to 1, y times sine of 2xy dy dx. And so what I'll point out about the way this integral is currently written is that this would require integration by parts. You essentially have y times sine of y. The 2x, as is written, doesn't really matter for the inner integral. So you certainly could do this one with integration by parts. However, I would also observe that the limits of integration are both constants, or all four are constants, right? 0 to pi, 0 to 1, meaning the area or region of integration is just a rectangle. And interchanging the limits of integration is literally just changing the order of the integrals. You don't have to do any drawing of pictures or thinking about what's going on. We can literally say that this is the same as the integral from 0 to 1, 0 to pi, y times sine of 2xy dx dy. If all your limits of integration are constants, you can change the order just by switching the integrals without doing any other thinking. So I might look at this first and be like, well, is that one easier to anti-differentiate? I think I can get away with that one without doing any integration by parts, at least in this inner step. So let's try doing it that way instead. So I'm really thinking of this as sine of a constant times x. So when I integrate this, I'm going to get the integral from 0 to 1, and then the antiderivative of sine of a constant times x. Well, the y, I should say, first of all, the y hangs out, and then the antiderivative sine of something is negative cosine of that stuff, and then I typically have to divide by the constant. The constant here is my 2y, so I'm dividing by 2y. As a reminder, just to make sure everyone's okay with that, when we do something like the antiderivative of cosine of 4x, we get something like sine of 4x divided by 4. Here, the thing that's acting like the 4 is the 2y. That's why we're dividing by 2y. Questions about that? All right. Oh, and of course, I should write my limits of integration. So we have from x equals 0 to x equals pi. And let's see, we can cancel y here and here. And we're going to get, let's bring out the negative 1/2. We got negative 1/2, the integral from 0 to 1. I'm going to plug in pi for x. You get negative cosine of 2 pi y minus, I'm going to plug in 0 for x and get negative cosine of 2 times 0 times y, which is just cosine of 0. Simplifying a little bit before I integrate, cosine of 0 is 1. So I get plus 1 there. So I should really rewrite this as negative 1/2 integral of 1 minus cosine of 2 pi y from 0 to 1. So switching the order of integration here saved us having to do integration by parts, which I think if I can avoid it, I always would. Let's finish this off. That's a 1, not a pi, sorry. Anti-differentiating again. Anti-differentiating mean we are taking the antiderivative, James. The antiderivative of 1 is y. The antiderivative of cosine of 2 pi y is going to be sine of 2 pi y divided by the coefficient of y, which is 2 pi, from 0 to 1. We plug in, we get negative 1/2 times 1 minus sine of 2 pi over 2 pi. The sine of 2 pi is 0. And then minus, plug in 0, 0 minus sine of 2 pi times 0 over 2 pi, which is also going to be 0. So end up with negative 1/2 times 1, which is negative 1/2. Does it make sense? Our answer is negative. Well, it doesn't not make sense necessarily. If you think about our original function, y times sine of 2x, it's certainly possible that somewhere, does it make sense there? Let's see. Now that I ask myself this question, if y is between 0 and 1, could sine be negative? No, I don't think 0 pi. Yeah, that's 2. There's a 2 there. Yeah, this can definitely be negative, so we're okay. So sine of 2xy when x is between 0 and 1 and y is between 0 and pi, you can definitely have positive and negative values for that function. So it's okay that our answer is negative. But if we had the thing I'm checking here is if my function was always positive, then the double integral of it or any integral of it should give you a positive area or volume. But since our function can be negative, it's reasonable to at least have the possibility of getting a negative answer. All right, so before we do another one, questions, observations about this one. I said before we do another one where we will have to do integration by parts. Okay, so I just want to say one more time, when these are constants, it's really easy to change the order of integration. When they're not constants, we have to do a little bit more work for that. So let's look at the next one here, which is right there. Let's do that one. Let's do that one. That one first? Yeah, that one first. Let's try the integral from 0 to 1, the integral from x to 1 of y squared e to the xy dy dx. And here's what I would say about this integral. When I look at this integral, I'm just looking at the insides. I'm just looking at the integral from x to 1 of y squared e to the xy dy. Because I know that that's what I'm going to have to deal with first if I leave it that way. Second of all, I'm ignoring the y. I'm just pretending like y is the number 6. So if I look at this, or sorry, apologies, x for the integral. Pretending like x is the number 6. So if I look at this, I see the integral of y squared times e to the 6y, which is going to require integration by parts twice. So I have a y to the second power times e to this constant times y. It's probably worth looking at changing the order of integration. Yes, we could do integration by parts twice. Do I want to do integration? No, not really. I would rather see if changing the order of integration is worthwhile here. I know it's work to do that, but it's probably worth it. It's maybe worth it, I should say. Probably is still too strong. It's maybe worth it. So to change the order of integration, we have to draw the region because it's not just a rectangle. So let's see. I'm always drawing the inner limits of integration first. Y equals x. And y equals 1. So that's my vertical rectangles are going as low as y equals x, as high as y equals 1, and they're going as far left as x equals 0, as far right as x equals 1. They're going that way. But now I want to change the order. So I draw my rectangle the other orientation. So I draw a horizontal rectangle. For my horizontal, which I'll do in red, my inner limits of integration are going to be from x equals 0 to x equals y. Still the same integrand, y squared times e to the xy with a dx. My outer limits of integration are how low my strip goes to how high my strip goes. Still 0 to 1. If you like, and I do like writing that we're going from a y equals 0 to a y equals 1, and then x equals 0 to x equals y. You don't need those. They're certainly implied by the fact that it's a dx there, so it's an x equals there and there. A dy there gives you a y equals and a y equals. But I like to write them. I find that helpful. Okay. Is this better? Maybe. It's certainly easier to do the first integration, right? If we integrate y squared times e to the xy with respect to x, really we just have a constant times e to a constant times x. So if I'm integrating e to a constant times x, I'm just getting e to that same thing divided by the constant. So when we integrate this, we're going to get the integral from 0 to 1. Oh, sorry, that's my thinner pen. And then integrating this part here, I'm going to get y squared times e to the xy divided by what? What are we dividing by there? Y, the constant, right? Because we integrated with respect to x, so we're dividing by the constant, which is y, which is great because one of those is going to cancel. That y will cancel with that y there. Ooh, I might no, oh no, I did. I was worried for a second I might have made a terrible mistake here, but I didn't. So if we plug in here, we're going to end up getting the integral from 0 to 1. Plugging in y for x, we're going to get y times e to the y times y. And plugging in 0 for x, we're going to get minus y times e to the 0. Seem okay? I think so, yeah. So now we've got the integral from 0 to 1 of y e to the y squared minus y. Y e to the y squared requires u substitution. Y is just easy to integrate. So if we do a u sub here, I feel like you get away without doing a u sub actually, but let's do the u sub real quick. So if I do a u sub, if u is y squared, du is 2y dy. So 1/2 du is equal to y dy. So let's write this as two integrals just so we can keep stuff straight. It's the integral from 0 to 1 of y e to the y squared minus the integral from 0 to 1 of just y. This is going to become the integral of 1/2 e to the u du. This we're just going to integrate and get y squared over 2 from 0 to 1. I would probably change my limits of integration here, except you know what? They're not actually going to change, which is kind of annoying, but it's actually what happens here. If y is 0, then y squared is 0 squared, which is 0. And if y is 1, 1 squared is still 1. So these limits of integration don't change. If it were me, I would probably be extra emphatic here. Be like, oh yeah, this wasn't a y equals 0 and a y equals 1. This is a u equals 0 and a u equals 1. Just so that the people who are grading my work know that I know what I'm doing. I'm not just ignoring the fact that limits of integration are changing, but not. Integrating this, we get 1/2 e to the u from 0 to 1 minus plugging in the limits of integration here, we get 1/2 minus 0. Finally, plugging in here, we get 1/2 e to the 1 minus 1/2 e to the 0 minus 1/2. 1/2 e to the 0 is just 1/2, so we end up getting 1/2 e minus 1/2 minus 1/2 is minus 1. Which is very slightly positive. Not that we really take a good look at that, but it is. Which it should be, because the function we're integrating is definitely positive all the time, or I should say non-negative. Y squared is always non-negative, e to the xy is always positive, and you multiply this together, it's always going to be non-negative. So cool, we avoided integration by parts. Yay for us. Is that always the goal? No. Is it sometimes the goal? Yes. Let's look at one more. One more and then we'll see. Okay, yeah, cool. Let's look at, say, something like this. The integral from 0 to pi over 2. The integral from 0 to the square root of x. 2y cosine of x dy dx. So looking at this one, I like to, before I start doing a problem like this, I really like to think about like what's going to happen if I don't do anything. So first of all, can I integrate this as is? Yeah, the integral of 2y times a constant with respect to y is just going to be y squared. times the constant. I'm going to plug in root x for y squared and get x. Plug in 0 for y squared and get 0. So I'll have essentially x times cosine of x, which I certainly can integrate using integration by parts. Is it worth trying to change this to the other way? Maybe, probably not. It could be. Let's see what it looks like, but we're probably going to end up doing it this way. But I will say, if you can integrate something one way without having to change limits of integration, it's usually good too. Like often these problems are written so that they can kind of be done. Usually they're written in a way so that they start off impossible. And then after you change the order of integration, they become possible, but still may be challenging. That is a hard question to answer with just a couple sentences, because really that's what 17B was all about, is learning kind of when we do what. And so I would say very generally, if you have a mixture of things, so a mixture meaning, so a logarithm or a power or a trig function or an exponential function like e to the x. So if you have a mixture of two of these things, we usually say two or more, but really you never have three of them together. If you have two of these things mixed together, I would first look for a U substitution. And if there isn't one that works or is obvious, then I would move on to trying integration by parts. So here, well, and we're not really quite there yet because we don't have a mixture technically because we have y's and x's. But after I did the integration here, I would have an x to the first times cosine, which is a mixture of a power times a trig. And it's not going to work out with a U substitution. So then I'm going to move on to integration by parts. But we'll get there in a second. But if I tried to change the order of integration, drawing my region, okay, I'm drawing first y equals 0 to y equals the square root of x. So I'm making vertical strips. And then my x's are just going from 0 to pi over 2. And then I'm changing it to look like this. So now my inner limits of integration are from x equals this function here. So instead of y equals root x, it's x equals y squared. And the right-hand boundary is x equals pi over 2. And then the left-hand or the outer boundaries, outer limits, is as low as 0, as high as, well, if x is pi over 2, y is going to be the square root of pi over 2. Just annoying. And then my integral would still be, my integram would still be 2y cosine of x. So yeah, we could do it this way, actually. If you integrated it this way, you would end up getting sine of x when you integrate that. And then you plug in the y squared, you have sine of y squared, which would lead to integration by part. There's a U substitution. So it's kind of interesting. It seems like you might be able to avoid integration by parts if you change the order and do the other thing, and then you get U substitution sometimes. It's not a guarantee it's going to go that way all the time. I still think it's worth doing this one with integration by parts. Yeah. So I started off with this integral. So in my inner limits of integration, inner integral, I have y equals 0, which is this line here, to y equals the square root of x, which is this curve here. And so since it's a y equals something to a y equals something, I'm drawing a vertical strip. And then I'm thinking about this strip going as far left as x equals 0 and as far right as x equals pi over 2. But then I'm going to switch it. So instead of drawing a vertical strip, I'm going to draw a horizontal strip. Now my inner limits of integration are, instead of being y equals something to y equals something, they're going to be x equals something to x equals something. The lower x boundary is x equal to y squared. The upper x boundary is x equal to pi over 2. And then my y boundaries are just how low this strip can slide and how high this strip can slide. Let's do it both ways. Maybe we'll do it this way first, because I would say without any really strong inclination to change it, I wouldn't. Right? Changing it is work, and this is definitely doable without changing it. So let's see what happens if we don't change it. we end up getting, let's see, I'm going to integrate with respect to y. So I'm going to get the integral from 0 to pi over 2. Anti-differentiating 2y gives me a y squared times the constant cosine of x from y equals 0 to y equals root x. And then plugging in those limits of integration, I get, well, square root of x squared is just x times cosine of x. I'm not going to write it, but if we plugged in 0, we would get minus 0 squared times cosine of x, which is just 0. I'll write it. So there's the thing we need to integrate. But now integrating x cosine x does require integration by parts. Why not use substitution? Well, because there isn't a good choice for you here. Right? There isn't a choice for you, well, whose derivative is also there. I mean, and you never want to pick u equal to x if you're doing u substitution. It just changes the letters. It doesn't actually change anything else. So this is definitely integration by parts. And I feel like I made my feelings clear. Maybe I haven't. I'm going to make my feelings clear about integration by parts for a definite integral. You should do it indefinitely first, meaning I would much rather just do the integral of x cosine of x without the limits of integration, and then at the end I'll kind of fix it all. So I'm going to let u equal x because that's the first thing that appears in my LATE acronym, the any power of x thing. And then dv has to be all of the rest. So when you're doing integration by parts, once you have chosen a u, everything else is decided for you. I chose u equal to x. I am required to pick dv equal to everything that is multiplied by x in this integral. So that's going to be cosine of x times dx. All that. So that u times dv is everything inside of my integral. I get no choices, no freedom once you're doing integration by parts and you pick the u. Du is the derivative of x times dx. V is the antiderivative of cosine of x, which is sine of x. And then we just throw everything into our formula, ultraviolet super voodoo. UV minus the integral of V du. The antiderivative of sine is negative cosine. So we're going to end up getting x times sine of x minus negative cosine of x, which is plus cosine of x. And then I'm going to go back and say that this thing here that I was actually trying to find, the integral from 0 to pi over 2 of x times cosine of x dx, is equal to this antiderivative evaluated at the endpoints. I like doing it that way. I just find it to be the cleanest way I'm capable of doing it. I don't want to carry the 0 to pi over 2 here, 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 and like it becomes messy for me. So then plugging in, we get pi over 2 times sine of pi over 2 plus cosine of pi over 2 minus 0 times sine of 0 plus cosine of 0. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. Sine of 0 is 0. Cosine of 0 is 1. So we end up getting pi over 2 times 1 minus 1. Which I would probably leave like that, but some people would probably prefer to write it as pi minus 2 all over 2. Another fine way of writing it if you prefer. Should we? Oh yeah, question. Mm-hmm. I plug in the square root of x for y.
So square root x square is x.
Right.
Times 1
Times cosine of x.
y equals x.
Well, because it's still there. Right. I mean, so right here, right, I'm just plugging in square root of x for y. Right, because remember, These are y limits of integration. This is another reason why I really like to write y equals and y equals. So that when I plug it in, I know I'm only plugging in for the y's. No, it depends. Here, x is on the outside, not over here. We switched it over here. So it really is just however it's written. I should say whichever d whatever occurs last, that's the one on the outside. Yeah. Sorry to be so, I want to be very firm that it is a no, it is not always one thing on the outside.
One of the conceptual question, like when we were doing one-dimensional images, you know, with respect to images, yeah, right? So we were only doing it from one dimension, but now because this is two-dimensional, there's double intervals because we're doing it in x and y, right?
Correct. So before it's kind of like we were integrating a curve over a line. And now we're integrating a surface, kind of like if you have like a blanket stretched out over your floor and you like pulled it up and like that could be your surface and the floor area is the area you're integrating over.
Yeah. And so before it was vegetables, now it's more of like
Yes, exactly. So the thing that I'm not drawing in either of these pictures is the surface function that's representing the height. So the whole idea here is that this is the region we're integrating over. And then what we're really doing is say, okay, well, each of these little squares, there's really exactly like you said, a rectangular prism shooting out of it that is the height of the function at that particular little square part. And so maybe it's like shorter over here. Right. Exactly. Let's go ahead and do this one the other way, just to see that it doesn't matter which way you do it, in that we should get the same answer, although it does kind of matter because sometimes it's impossible one way, sometimes it really just sucks doing it one way. Well, let's try it. Let's try it the other way and we can decide if we like it better one way versus the other. Again, it really just depends on what you've got. But sometimes either way will work. So if we try doing it this way, the integral from 0 to the square root of pi over 2, integral from y squared to pi over 2, 2y times cosine of x dx dy. Now if we're integrating with respect to x, the 2y is a constant that's going to hang out. We're going to get the integral from 0 to the square root of pi over 2. The antiderivative of cosine of x is sine of x, so we're going to get 2y times sine of x, evaluated between x equals y squared and x equals pi over 2. dy. Plug in integral from 0 to square root of pi over 2, 2y times sine of pi over 2, which is 1, minus 2y times sine of y squared. Let's just talk about what this u sub is going to be. So that's definitely going to be a u sub. 2y times sine of y squared. You're going to let u equal y squared, and du is going to be exactly 2y dy. So really integrating this is really like integrating sine of u. And what's the antiderivative of sine of u? Exactly, negative cosine of u. So the antiderivative here should be negative cosine of u, which is our y squared. Let's check that to see if it works. If I take the derivative of negative cosine of y squared, I should get positive sine of y squared times 2y. Oh, that's exactly that. We're good to go. And then the minus will actually make it a plus. So integrating this without doing all the u substitution really, and also noting that sine of pi over 2 is equal to 1, the antiderivative of 2y is y squared minus cosine of y squared. From 0 to the square root of pi over 2. Again, when I do something like that in my head, or pseudo in my head, I kind of like to double check and make sure it's right. So just to check again, if I take the derivative of y squared, I do get 2y times 1. If I take the derivative of cosine of y squared, I do get negative sine of y squared times 2y. So that's checking out in my book. So now let's plug in, I get the square root of pi over 2 squared plus cosine of the square root of pi over 2 squared minus 0 squared plus cosine of 0. And that's exactly equal to pi over 2. Cosine of pi over 2 is 0. Minus 0 plus 1 is minus 1. Same answer as doing it the other way. So either way is fine. If either way is fine, meaning if either way is an option, usually one of them is not going to be so much worse than the other. But sometimes, many times, one way is not going to be an option. That is a matter of your instructor's preference. So if I was asking a question on a test, I would write it in the most ambiguous way possible because I feel like it is the onus of the student to have to be able to see that you can't do it one way. It also kind of depends. Like some problems, like we've seen here, can be done either way. Whereas let's look at something else. We'll do one more. So I have one more. We'll try and keep these things in order. This is going to be challenging. Okay. So let's say we had something like, the integral from 0 to 3, and then the integral from e to the x to e to the third of y minus 1 over the natural log of y, dy dx. So at the very first juncture here, I'm trying to anti-differentiate y minus 1 over the natural log of y. I got nothing. I have no idea. I don't even know if you can integrate that, to be perfectly frank. If it was like natural log of y over y, sure, we could let u equal natural log of y, du is 1 over y. But if something looks like an integral you've maybe never really encountered before, or there doesn't seem to be a good, easy u substitution or a straightforward integration by parts, like if your first antiderivative just looks kind of impossible, it's probably a good idea to check at least to see what happens if you go the other way. Also, you can see that if we change the order of integration, integrating with respect to x first is just going to multiply that whole thing by x. There's not going to be anything else to do. So that'll get you at least something that might then cancel out nicely. So let's change the order of integration. We're going to change it up. We have to draw the region. Okay. I'm always drawing the inner region, the inner intervals first. So y equals e to the x is something we know. It's like this. Let's draw it in blue. I like blue. And then y equals e cubed is a horizontal line, right? E cubed is, I don't know what it is. It's 20 something ish, but it's definitely just a straight horizontal line. It's not a function. It's not a variable function. It's a constant function. And that is a straight horizontal line. We will pretend that all is horizontal. And then we're going from x equals 0, which is just the y-axis, to x equals 3, which odds are is where these two functions intersect. And of course it is, because if x equals 3, then e to the third is going to equal e to the third. So these definitely intersect at 3 comma e to the third. I wouldn't even really draw the line x equals 3 because it's kind of just the end of that boundary there. That would have been how we set it up using vertical strips, because we're starting with y equals bottom to y equals top, and then we're going as far sliding left and right. But now I want to change it, so I'm going to change the orientation of my strip from vertical to horizontal. So my left boundary is x equal to 0. My right boundary is, instead of y equals e to the x, it's going to be x equal to what? Yeah. Natural log of y. So, right, before our limits were y equals low to y equals high, now our limits of integration are going to be, our inner limits of integration are going to be x equals low value to x equals high value. Right, x is bigger to the right, smaller to the left. Y is bigger to the top, smaller to the bottom. And then same function, but now it's a dx. And now my outer limits of integration are, this strip is certainly going to go as high as y equals 3. Oop, not y equals 3. Y equals e to the third, right? That's how high this goes. How low do we go? It's like a limbo question. How low can you go? How low can we go? Can we go all the way to 0? No. How low do we go? Yeah, down to 1. This looks promising because I can see that when we anti-differentiate, we're going to get x times that stuff. Then we're going to plug in the natural log of y for x, and it's going to cancel the natural log of y in the bottom. And we're going to subtract and plug in 0 for x, which is just going to give us the 0. Sure. So to solve, so basically, whenever you're changing your limits of integration, the things that are functions of each other, you have to solve for the other variable. So I took y equals e to the x, and there's many ways people like to do this. I just took the natural log of both sides in my head. And the natural log of e to the x is just x. Okay. So now we're going to anti-differentiate. And again, anti-differentiating this with respect to x is about as easy as it gets. We're going to have the integral from 1 to e cubed. The antiderivative of this function of y with respect to x is just going to be y minus 1 over natural log of y times x, where x goes from 0 to natural log of y. Plugging in, you get y minus 1 over natural log of y times natural log of y minus, it feels kind of silly to write this all out, but that's what we get. That's just going to be 0 because anything times 0 is 0, and that's just going to be y minus 1. So we really just get to have the integral from 1 to e cubed of y minus 1. I feel like I shouldn't even write the rest because the rest is really straightforward. I'm going to write it anyway, but you know, you get y squared over 2 minus y from 1 to e cubed. Plugging in, you get e cubed squared over 2 minus e cubed minus 1 over 2 minus 1. And I guess if you really wanted to simplify this, you could write it as e to the 6th over 2 minus e cubed. 1/2 minus 1 is negative 1/2, so plus 1/2. So again, if something looks impossible at the get-go, it's probably a sign that you should change the order of integration. And I know in some of the homework problems, they definitely tell you to evaluate the double integral by changing the order of integration. But just be aware that sometimes you could encounter a problem where they're not going to tell you you need to do that, and you still need to do that because it won't work otherwise. All right. It feels like enough double integration. Doesn't mean we can't ever come back to it, but we should talk about other things. Yeah. So now for what I kind of tend to think of as a lot of the real meat or interesting part of what 17C is. Yeah. Let's go ahead and remind ourselves of some stuff from 17B. So I'm just going to remind you. So recall. When someone says recall, it means here's some stuff that you were supposed to have learned. Hopefully you remember it. I'm going to mention it briefly, and then the expectation is you know it. That's what, when your teacher says recall, that's what they mean. You know this stuff. I'm just reminding you that you know it. And yes, we can talk about it more in depth if we need to. So in 17B, we had this equation. I mean, we had lots of equations, but one of the things we talked about was if the rate of change of x is proportional to x. So the rate of growth or change, whatever way you want to say it, the rate of growth of x is proportional to, just meaning it's a multiple of the population size, x. That's what this equation, that's what this differential equation means. Dx dt equal to a multiple of x is just saying the rate of growth is some multiple of the population size. And as the population gets larger, the rate of growth increases because when there's more people, they make people faster because there's more of them to make people. Then they make more people, and then it keeps increasing like that. So the thing I want you to really know is that this sort of differential equation has a very specific type of solution. Let's in fact solve it. So we're going to solve it by separating variables. So if I have dx dt equal to a times x, I want the x's on one side and the t's on the other side. The x's should end up on the, and we want the d whatever's to always be on the top. So I'm going to divide both sides by x and multiply both sides by dt. So they have 1 over x times dx equal to a times dt. And then we're going to integrate both sides. We integrate 1 over x, I get the natural log of x. And we just kind of ignore the absolute values. I know it's kind of hand wavy, but trust me, you don't really need them. Or really, they get magically kind of taken care of by the constant is actually what's happening. The antiderivative of a times t dt is just a times t plus a constant. We're going to solve for x. So we're going to e both sides. So e to the natural log of x equals e to the at plus c. E to the natural log of x is just x. E to the at times e to the c is e to the at times e to the c. And typically we think of e to the c as just another constant, right? If c was 5, e to the 5 is also a constant. And I'm going to annoyingly also call it c, because that's what people do. So we're going to say this is a new capital C, and we're going to rewrite this as x of t, x is a function of t, is equal to capital C times e to the at. So the thing I want you to really, really know about this is that when you have this sort of differential equation, where the rate of growth is proportional to the population size, that really means you have exponential growth. So this leads to exponential growth. I should be slightly more specific here. It's exponential growth if the constant proportionality is positive. It's exponential decay if that proportion is a negative number. But when we talk about populations, we usually think about them growing. So yeah. If A is positive, you get growth. If A is negative, you get decay. All right, so where are we going with this? Well, how much time have we got? Oh, we got enough time. We got 20. We got 35 minutes. Yes. So we're going to come back to this. Don't worry, it's not going away, but we're going to take a little side trip and then we'll come back. More 17B review. Here's a matrix. -1, 2, -3, 4. Let's find the eigenvalues. So I will encourage you all, in your textbook, there's lots of matrices like in the problems. If you have time to practice, definitely practice finding eigenvalues. It's something you want to be able to do relatively quickly because you're going to do it often in the next 4-ish weeks. Or 3 to 4 weeks. So eigenvalues. To find the eigenvalues, we're going to take the determinant of A minus lambda times the identity matrix. Normally, so I'm going to write it out, but well, I'll write it out and then we'll talk about how we get there. So that's the determinant of the matrix A, -1, 2, -3, 4, minus the matrix where the identity matrix, which is the matrix with 1s on the diagonal and 0s everywhere else. For 2 by 2, that's just a 1, a 1, a 0, and a 0, like that, times lambda. And then, again, writing way more steps than you ever would really, I would write this as -1, 2, -3, 4, minus lambda, 0, 0, lambda. Finally combining those into one matrix, determinant of -1 minus lambda, 2, -3, 4 minus lambda. So really what you should do after you write out determinant of A minus lambda I is jump straight to saying it's the same matrix A, but in the diagonal spots, you're going to subtract lambda. So, oh yeah, -1 minus lambda, 2 stays as 2, -3 stays as -3, and 4 minus lambda. So you're going to set that determinant equal to 0. And then you're going to solve for lambda. So when you take the determinant of a 2 by 2 matrix, it's really not terrible. It is terrible for larger matrices. Like if it was 3 by 3 or 4 by 4 or 5 by 5 or anything bigger, the determinant is a lot more complicated of a calculation. But for a 2 by 2 matrix, it's actually really, really straightforward. The determinant is always the product of the diagonal matrix, the diagonal elements. So -1 minus lambda times 4 minus lambda minus the product of the off diagonal elements. 2 times -3. And we're setting that equal to 0. Then we're going to solve. So let's see, multiplying this out, we have a -4 minus 4 lambda plus lambda is -3 lambda plus lambda squared plus 6. Yeah, okay. And then that's still equal to 0. And then simplifying this, writing it in the more standard way, I got lambda squared minus 3 lambda, 6 minus 4 is 2. Finally, factoring, we've got lambda minus 1 times lambda minus 2 equal to 0. So our eigenvalues are lambda equal to 1 and lambda equal to 2. It is pretty typical to label these as lambda 1 and lambda 2, not because they're equal to 1 and 2, but because there's a first one and a second one. So it would be pretty common to be like, there's lambda 1, there's lambda 2. Doesn't really matter which one you call which one. It'd be annoying to call lambda 1 equal to 2 and lambda 2 equal to 1, so you wouldn't usually make that choice. But if the values are like 5 and -3, I would call lambda 1 5 and lambda 2 negative. Like, it doesn't matter which way I pick them. Yeah. Sure. Okay, we're almost there, I promise. We're coming back around to what we were talking about before. So now I want to find the eigenvectors. The eigenvectors are the vectors that are solutions to the matrix A times the eigenvector equal to the eigenvalue times the eigenvector. So there should be a vector. So if you take the matrix A and multiply it by that vector, it's equal to the eigenvalue we just found, either one of them times that, well, I should say either one of them for specific different vectors times that vector. And I feel like we don't really have enough room here. So let's give ourselves a little bit more room. So I want to solve for lambda 1 equal to 1, A times the vector equal to lambda 1 times the vector. The vector is the thing I'm trying to find. Everything else I'm plugging in for. So I'm really trying to solve my matrix A, -1, 2, -3, 4, times my unknown vector, which people either write as like xy or x1, x2, equal to 1 times the unknown vector. This is one way of doing it. This is the way I prefer to do it. I will also show you the other way of doing it for the next eigenvector. Typically here, you can get away with using just one of the equations, meaning if you actually multiply this out, you have this row dotted with this column equal to 1 times this first entry. So the first row gives us -1 times x plus 2 times y equal to 1 times x. And now I'm going to try and get a relationship between x and y. I'm going to add x to both sides. 2y is equal to 2x, divide both sides by 2, y is equal to x. And that equation, y equal to x, is your eigenline. We'll talk about that more later, but any vector that starts at the origin and ends on a point on that line is an eigenvector. So what's a point that's on the line y equals x? Any point. 1, 1. What's another point? How about another one? Give me a -1. Great. All those things you just said are eigenvectors of this associated with this eigenvalue. Now, are we going to write all of those? No. We're going to pick one. The one we're usually going to pick is the one that has the smallest possible integer values. So the eigenvector that we're going to write here, v sub 1, is the eigenvector 1, 1. Technically, any multiple of that, with one exception, would also be an eigenvector. 2, 2, 3, 3, 1,000, 1,000, whatever you like. The only eigenvector you can't pick is 0, 0. It's not a good choice. It's not good because it's actually an eigenvector for anything. So okay. So that's the eigenvector, or the family of eigenvectors associated to the eigenvalue lambda equal to 1. Let's find the other one for lambda equal to 2. Now I'm going to show you the alternate way of doing this, which is not my favorite, but it is some people's favorite. So instead of solving a times v equal to lambda times v, you can alternatively solve a minus lambda I times v equal to 0. When I say 0, I mean the 0 vector, 0, 0. So writing it this way, it's, well, let's see, and here lambda is equal to 2. So it's the matrix A, which was -1, 2, -3, 4, minus, I know I'm doing the thing the long way, times the vector v, which I'm still going to call xy, equal to the 0 vector, which is 0, 0. And then, of course, we should have just skipped writing it this long way and written it as -1 minus 2, and 2 minus 0, and -3 minus 0, 4 minus 2. The thing that I think is kind of nice about doing it this way, even though it's not my preferred way of doing it, is when you do it this way, you typically get that both rows are kind of the same or multiples of each other. So it's relatively obvious that no matter which row you use, you're still going to get kind of the same equation. Whether I use the first row and get -3 times x plus 2 times y equal to 0, or I use the second row, -3 times x plus 2 times y equal to 0. Either way, it's the same equation. Either I'm going to solve for y. You looking for something?
Yeah, I think I'd look fine.
Oh. Oh, okay. Yeah, I see one right there. Yeah. So I would solve for y typically. So 2y equals 3x. I actually probably wouldn't go any further than this unless I was specifically asked to find the eigenline. So I'll just point out that y equal to 3/2 x is the eigenline. But really, right here is a great place to make a choice for x and y. And the great choice you typically want to make, the nicest choice that people want you to make, is the one where x and y are each other one's coefficients. So I'm going to pick x equal to 2 and y equal to 3. Because 2 times 3 is 6 and 2 times 3 is 6. So they are equal to each other. So my eigenvector here is x equal to 2, y equal to 3. Which you can see totally works, right? If you pick x equal to 2 here, 3/2 times 2 is 3. And again, technically any multiple of that would also be fine. You could have picked 4, 6, or 10, 15, or any other multiple. Except for 0, 0. All right. I promise you, we're going to come back around to the differential equation part as soon as we can. It takes a little bit. There's a lot of machinery that's built up into this. We're almost there. So let's let x of t equal the population of wolves, and y of t equal the population of deer, or more generally, predator and prey. And let's say that dx dt, well, not say, I mean, when you write dx dt, that is the growth rate of x. That's the growth rate of x. And similarly, dy dt is the growth rate of y of t. We would expect these populations to depend on each other, right? If the population of deer gets really, really big, then the population of wolves is going to grow because there's a lot of deer for them to feed on. But then the population of wolves is going to get too large, and there's going to be too many wolves, and they're going to kill a lot of the deer. Population of deer is going to be very small, and then the population of wolves is going to follow that because there's not going to be enough deer for them to eat. So it's kind of like this ebb and flow of both populations. I mean, this example probably doesn't display that, but it's probably something that's kind of sinusoidal, where it's like the population of deer increases and the population of wolves is increasing after it. They kind of probably follow each other, something like this. I don't know the biology at all, really. I'm just making stuff up, but it seems reasonable that it would go like that. So let's say we have the following. Let's say that dx dt is equal to negative x plus 2y, and dy dt is equal to negative 3x plus 4y. With initial conditions, x at time 0 equal to 2, y at time 0 equal to 4. Also something to think about. If y were equal to 0, right, if there were no deer, then dx dt, the rate of change of the population of wolves, would be -1 times the population of wolves. So their population would be decreasing because there's no prey for them to feed on. And oppositely, if x was 0, dy dt would be 4 times y. The population of deer would increase because there wouldn't be any wolves to prey on them. So these equations seem sensible enough. All right, so now, finally, we're getting back to where we were, which is that I'm going to rewrite, So I'm going to rewrite this equation. Oh, sorry, there's something in the chat. Can we please lower the page? Yes, sorry. Yes. Sorry. So I'm going to rewrite this equation. You can say lower, maybe you like, yeah. There. Okay, we can see all the things. So we're going to rewrite this equation as a matrix equation. dx dt, dy dt is a vector, and it's equal to the coefficient matrix I think sorry, I'm not sure what you're referring to exactly, Jessica, or whoever that was. Give me a second. So this coefficient matrix, -1, 2, -3, 4 times x and y. So you're trying to see what's in this page or in the previous page? I think you said the previous page. Sorry. Sure. So there's the previous page. Not sure what you're trying to see specifically here. That's what it looks like. And I'll point out that this matrix that we have, cool, is the same matrix we were just talking about by design. So essentially what we're trying to solve here is, if I think of this here as the vector x, actually I'm going to call it, and this is where I should have used different notation. Oh well. I'm thinking of this as a vector x of t, and this is the derivative of that. Well, look, I'm essentially saying the derivative of my thing is a constant times my thing. And that kind of equation has the same kind of solution as the problem we did at the very beginning, where dx dt was equal to a times x. We're going to get some sort of e to the a times x times a constant solution. But e to a matrix is a different kind of animal, but luckily the solution is easy to kind of deal with. So, just like how dx dt equal to a times x has x of t equal to c e to the ax as a solution, dx dt equal to the matrix A times x of t has a solution that looks like x equal to c e to the a times t. But the problem is you can't really have a matrix as a power. So what we do is we kind of, in some sense, replace the matrix with its eigenvalues. So actually, but that's weird. So actually what we do, we write our solution as, and you're going to want to memorize this equation because it's going to come up. You can't help yourself but memorize the equation I'm about to write. The solution is going to be x of t as a vector is equal to c1 e to the lambda 1 t times v1 plus c2 e to the lambda 2 t times v2. If you know the first half of it, you know the second half of it. They're just the same with different subscripts. So here's what that means for our problem here. We know the eigenvalues, we know the eigenvectors. I know they're on a different page, but we're going to get here that our solution, x of t, which is equal to xy, is equal to c1 e to the lambda 1 was 1 times t, and v1 was the vector 1, 1, plus c2 times e to the lambda 2 was 2 times t, and the second eigenvector was, I don't remember if it was 2, 3, or 3, 2. I guess it's written right there. It's 2, 3. That is the general solution to this system of differential equations. Now, I will say we should actually get a particular solution because we were also given initial conditions. I'll try not to scooch this off the page too much here. So I'm going to write this again so that we have it here. Oops, come on, James. So we have x of t equal to c1 e to the t times 1, 1 plus c2 e to the 2t times 2, 3. Now, I'll remind everybody that this is the general solution to our system of equations, which was dx dt equal to negative x plus 2y, and dy dt equal to negative 3x plus 4y. And our initial conditions, if I can remember what they were, or I can find them back on the previous page here, was x of 0 was 2, y of 0 was 4. So just like with most differential equations, these initial conditions, these are what allow us to solve for our constants. So these will be used to solve for the constants C1 and C2. Okay. It's actually not that bad to solve for them. So what we're going to do is we're just going to say, well, I know that x of t is equal, oh, sorry, I thought raising my hand, sorry. So x of t is this. If I plug in 0 for t, x of 0 is going to equal c1 e to the 0 times 1, 1 plus c2 e to the 2 times 0 times 2, 3. And that should equal the vector 2, 4. E to the 0 is 1. Which is why you almost always be given time equal to 0 as your initial condition, because otherwise it's still a little messier to solve it. So what I've really got here is C1 times 1, 1 plus C2 times 2, 3 equals 2, 4. There are lots of ways to solve this. Some people like to make a whole matrix equation out of it and find the inverse and do a whole thing. It's usually easier just to like write it out as C1 plus 2C2 equals 2 and C1 plus 3C2 equals 4. And then solve that system of equations by either adding or subtracting them together. If we do the first one minus the second one, the C1s will cancel. C1 minus C1 is 0. 2C2 minus 3C2 is negative C2. And 2 minus 4 is negative 2. So C2 is equal to 2. And if C2 is equal to 2, plug that back into either one of these to solve for C1. C1 plus 2 times 2 equals 2. Oops, so C1 is equal to 2 minus 4, which is -2. We can double check. -2 plus 4 is 2, check. -2 plus 6 is 4, check. So we found the particular solution. So, oh yeah, Jasmine. Which numbers? Yes.
The ones in the matrix.
Sure. Let's back up a little bit here. Oh my gosh, calm down. Okay. So let's go back to where we started this whole. So we had X and Y as the population of wolves, population of deer, and we made up a function. We said the rate of growth of wolves was -1 times the population of wolves plus 2 times the population of deer. And the rate of growth of deer was -3 times the population of wolves plus 4 times the population of deer. And then we rewrote that as a matrix equation. So we took that equation here, and actually I'm going to write it again right here. And we said we can really write this as the matrix of the derivatives, dx dt, dy dt. I should say the vector really, although a vector is a matrix, equal to what I'm calling the coefficient matrix. So it's just all the coefficients of x and y in order. So make sure when you write this coefficient matrix, you are writing the x coefficients first, the y coefficients second. So it's -1, +2, -3, +4. Times the solution vector x, y. So check this out, right? This is dx dt is equal to -1 times x plus 2 times y, which is exactly what we've got right there. Dy dt is equal to -3 times x plus 4 times y. And then we said, okay, well, we really have something very, very similar to dx dt equals a times x. We have the derivative of the vector x equal to a times the vector x.
Why did you call it vector then?
Because I was lazy. So normally other people, myself included, would have often made the choice to call this like x1 and x2 to more appropriately call this x. But just because we're trying to pick a name for it, it does usually get called the vector x, even though I'm using x and y here. But that's why it would have been a better choice on my part to use x1 and x2 instead of x and y, but I didn't. But really just because we had to pick a name and it's a convenient. And then we said, well, just like this equation having a solution that's an exponential equation like that, we're expecting this equation to also have an exponential type equation like this, except we can't have e to a matrix because it's kind of weird. So what we do instead is we use the eigenvalues of that matrix, really because there's a lot of higher level math people have done to show that this works. And so then we're rewriting our equation instead of as just c e to the a times x, it's c e to the constant times a variable times the first eigenvector plus c e to the second constant or second eigenvalue times our variable times the second eigenvalue. No, don't be sorry.
We just need to basically notice.
Yeah, it comes up a lot. You're going to want to know it for sure. And really, you only have to memorize half of it, right? Because once you know this half, the second half is just the same, but with twos. And then we plugged in all of our things. So we plugged in the lambda1 equal to 1 and the corresponding eigenvector v1 equal to 1, 1. And the second eigenvalue lambda2 equal to 2, and the corresponding eigenvector was 2, 3. And those are back from the work we did before all this, right? We were just kind of remembering what we did in 17b. And then we use the initial conditions, which were again given to us, that when t equals 0, x is 2, and when t equals 0, y is 4, to solve for the constants c1 and c2. So we plugged in 0 for t, and we set this whole equation equal to what you get when you plug in 0 for t. And then we said, okay, well, e to the 0 is 1, e to the 0 is 1. So I have c1 times 1 plus c2 times 2 equal to 2. And c1 times 1 plus c2 times 3 equal to 4. That's how I got these two equations here. C is not given. We're finding C. T, right, so this information is saying that when t equals 0, x equals 2, and when t equals 0, y equals 4. Right? We're plugging in a value for t and getting out a value for x or y. We use these equations to solve for the constant c1 and c2. And then we're going to do the last thing here, which is to say, okay, so our particular solution now Again, just like when you solve a differential equation and you have a general solution which has a constant, and then you find the particular solution by finding the constant values, you then have to go back and plug those into your actual general solution. So we're going to take this general solution here, and we're just going to plug in what C1 and C2 are equal to. So I'm going to say that x of t, which is equal to x of t, y of t. Notice the difference here. This x of t has an arrow above it, meaning it's a vector. This x of t does not, meaning it's an entry. That's going to be C1, which was -2 times e to the t times the vector 1, 1, plus C2, which was, I believe, 2. Yes, it was. Times e to the 2t times 2, 3. And this is the solution to dx dt equal to -x plus 2y, dy dt equal to -3x plus 4y, with the initial conditions x of 0 equal to 2, y of 0 equal to 4. Now, something interesting here. You can show this as a solution. Like, you can actually go back and be like, well, James, I know you're saying this thing is a solution, but is it really the solution? Well, yeah, because here's what we're actually saying. In the first row of our solution, and it's good to be able to look at these things row by row. So the first row is just the top part. So it's -2 e to the t times 1 plus 2 e to the 2t times 2. And the second row of our solution is just y of t equal to -2 e to the t times 1 plus 2 e to the 2t times 3. And not that you ever should have to do this, but if someone wanted you to, you can totally check to see, okay, well, is it really true? Does dx dt actually equal -x plus 2y? Well, let's take a look. The dx dt, if I just take the derivative of this, I get -2 e to the t, and I get the derivative of e to the 2t is going to multiply by another factor of 2. So I'm going to get e to the 2t times 2 times another 2 and another 2. So I'm actually going to get 8 e to the 2t. Is that equal to -x plus 2y? Well, -x plus 2y is kind of annoying to deal with. It's -2 e to the t plus 4 e to the 2t plus 2 times y is 2 times -2 e to the t plus 6 e to the t. 2t, sorry. All right, let's multiply it out and see what we get. I get 2 e to the t minus 4 e to the t, so I get a -2 e to the t, and I get a -4 e to the 2t plus 12 e to the 2t, which is 8 e to the 2t. And oh yeah, those are exactly the same. So it really is true that dx dt is equal to -x plus 2y. And I don't want to check it because it's annoying, but I probably will anyway. It is also true that dy dt, which is equal to the derivative of this, so it's going to be -2 e to the t plus 6 times e to the 2t times 2, so 12 e to the 2t. That is going to equal -3x plus 4y. Which again, -3 times all this stuff here. So x is still what it was, -2 e to the t plus 4 e to the 2t plus 4 times -2 e to the t plus 6 e to the 2t. And if we multiply this out, -3 times -2 is 6. 4 times -2 is -8. 6 plus -8 is -2 e to the t. -3 times 4 is -12. 4 times 6 is 24. -12 plus 24 is +12. So 12 e to the 2t. And those are exactly the same as each other. So yes, these things are equal. You should never have to check this because this process is the solution, right? As long as you've taken all the correct steps, you found the right eigenvalues and eigenvectors, once you get your answer, it is guaranteed to be correct as long as the steps along the way are correct. So once you get to this part here saying, you know, that's your solution, you shouldn't have to then check it by showing the derivatives are equal to the appropriate linear combinations of the other things. But it's nice to see it once. Be like, oh yeah, it really does give me an answer. Like this derivative is equal to this multiple of x plus this multiple of y. And this other derivative is equal to this other multiple of x plus this other multiple of y. So this is kind of what we're dealing with from now on for a while. We're looking at systems of linear differential equations. And these are linear because you just have a multiple of x plus a multiple of y for each of the differential equations and finding what the solutions of them look like. And we're going to be talking more about how we're going to interpret them. And really, I will tell you, most of the interpretation of whether we have stability or instability is based on the behavior of the eigenvalues. So if both eigenvalues are positive, it means one thing. If both of them are negative, it means another thing. If you have one of each, it means something else. And then we will talk about if the eigenvalues are imaginary. So we are going to have imaginary complex numbers. The eigenvalues are, so for these kind of things, it just means everything's like either going in or going out. But when you have complex numbers, the solutions spiral. So you have everything either spiraling in or spiraling out or spiraling like in a circle that doesn't go in or out. And that's going to be the case when you have eigenvalues that are imaginary numbers or complex numbers. So definitely it's going to, we're going to have a lot of solving of quadratic equations, right? Because if you think about our when we found the eigenvalues, right, we were solving way back here, right? We were solving this equation, which is always going to have a lambda squared and lower powers of lambda. You're always solving a quadratic equation. Sometimes it's going to factor, sometimes it's not going to factor, and you might get imaginary solutions. You might just get gross real solutions that have irrational numbers in them. So good time to brush up on your quadratic formula because it's definitely going to come back and we're going to use it. Next time we'll talk more about this, but we'll also talk about how there is kind of an alternative way of finding your eigenvalues, which some people consider to be easier. So we'll talk about it's using the trace and the determinant of the matrix. So if your teacher talked about that in 17B and you liked it, revisit it. If you have no idea what I'm talking about, don't worry about it. We will talk about it. It's not that hard to pick up on. And I probably tend to think it's an easier way of solving things sometimes. So yeah. All right. I will see you all on Thursday. Have a lovely Halloween. Thanksgiving's in a few weeks.